Good afternoon, everybody. Welcome back to DSP. Okay. A few announcements. Your midterm has been graded, so please pick it up during the break. And then otherwise, we are going to continue our discussion on filter design. Okay. Today I'll first try to finish our discussion, our introduction to infinite impulse response, IIR. That kind of filter. And then there's this other kind of filter called FIR, finite impulse response. I will enter that topic today. Okay, so please have a seat. All right, so otherwise, tomorrow we are going to have a discussion session, a follow-up discussion session. So please stay tuned. If you haven't looked at the problems, please take a look. And a bit about the grades. My TA told me that the average 平均多少分呢？83是 Okay, so the average is pretty high, and many of you get above 90. That's great. That's higher than I expected, but good job, everybody. So just please stay tuned, but and come to Thursday meetings, okay? Because Thursday meetings are important for you in terms of your final grades. Obviously, you know that, right? Whenever you ask a question, there's one extra point. So please, if you really aim high for this, really high in terms of the score, if you want to get the high score, please come to Thursday meetings. It should be pretty obvious now, okay? Any questions so far? All right, so let's take a kind of a preview where we're at last week. The Butterworth IR filter. Butterworth is a kind of filter which has an analog prototype, right? Analog prototype, and we have seen that if you arrange a transfer function in the S domain like that, putting several poles around one circle, and the circle has a radius of omega c. Okay? In the S-plane, not the Z-plane yet, okay? Not yet Z-plane, just S-plane. You place the poles like that, then from there, you can show that the magnitude square as a function of frequency turns out to has a very nice expression, which is monotonically decreasing with the corner frequency exactly placed at that frequency, omega c, okay? So that's a fairly nice property, and here n denotes the order, okay? Make n bigger, you get a faster transition, okay? And you can check that. So last week, we spent much time on checking why this is the case. This is not that trivial, but hopefully either n could be even, n could be odd. This expression is valid for both cases, okay? So really, just we have checked that if you just place a poles like that around the one circle, and you get this very nice monotonically decreasing magnitude response, which is very nice. And then, yeah, so we have made sketches of how we have seen how the response varies as n increases. With the same corner frequency, when n increases, you get a narrower transition. The transition becomes narrower. Okay, it dropped the gain drops from 1 to 0 more. Faster, more rapidly. So now we've done that sketch, and now the question is how do we make use of this prototype and transform it so that we have a digital filter? How to go from analog to digital? And the answer is using bilinear transformation. So let's take a look. So we take a look at here. Bilinear transformation is a function from Z to S. We can define S as a function of Z. Define S as a function of Z. So there will be 1 minus the inverse, 1 plus the inverse, and there's a parameter 2 divided by TD. Okay. So that's just simply a definition, and where TD, as you will see, can be adjusted. Okay, can adjust this, and then with this transformation, we can go from analog to digital using this equation. Okay, let's say H is the prototype. Okay, H is a function of S, so H is in the S domain. Now, whenever you see S, just substitute, make a substitution, rewrite S as a function of Z. Is that clear? 重写一遍啊。Whenever you see S, rewrite S as a function of Z, and then the result will become a function of Z. So this composite function 就是结合啊，函数的结合啊。Composite function G, let's call it G. G will be, we argue that G is already a design. It's that simple. Coming from, just start with an analog prototype, and then by substituting S as a function of Z, 就是变数变换啊。By doing this substitution, we have a function of Z, and we claim that G of Z, you can just organize the top and bottom. In general, it's going to be our old friend B of Z divided by A of Z. It'll be, you can write it in that format, B of Z divided by A of Z. And then we know that when you reach that expression, when you have that expression, then it's rather straightforward to find the difference equation corresponding to BZ divided by AZ. Yeah? So, okay, so we call that already a design. So today, our job is to take a closer look. How come we say this is a design? How come we, because like operation-wise, in terms of just doing the calculation, it's pretty straightforward. In terms of doing the calculation, just follow the steps, find B of Z and A of Z. Calculation could be tedious, 有可能很琐碎, but it's rather straightforward. 琐碎但是还蛮直截了当, okay? So operation-wise, calculation, in terms of calculation, it's not that hard. But I think the key point I want to deliver today is why can we say this is a design? Why? Yeah, should be pretty surprising, okay? But here is a nice little exercise which we might use from time to time. If S is a function of Z, and bilinear transformation, bi means bidirectional, right? Yeah. So Z can also be expressed as a function of S, okay? Let's maybe work this out. There's an exercise. We can try to say, find Z as a function of S. So if S equals to 2 divided by TD, 1 minus Z inverse, 1 plus Z inverse, then TDS divided by 2 is 1 minus Z inverse, 1 plus Z inverse, right? So from there, we can say, let's work this out, okay? TDS multiply, how about we do this? Equals 1 minus Z inverse. And therefore, what's next? So let's move 1 minus TDS divided by 2 to the right. Okay, there's things with this term. And on to the left, we have Z inverse, what? Z inverse times 1 plus TDS divided by 2. So we are almost there. So therefore, Z is 1 plus TDS divided by 2 divided by 1 minus same thing. Okay, so here is just a nice little quick exercise. We can also express Z as a function of S. So in general, bilinear transformation is a mapping from S domain to Z domain. And since the inverse function has been written out, so we have found the inverse transformation. So this is basically a one-to-one mapping. Okay, one-to-one mapping between the S-plane, real S, imaginary S, between S domain and Z domain. Okay, so we are gonna leave everything for now on the board. I will come back to my plot later. Right? Any questions so far? S as a function of z, z as the inverse function can be also derived. Okay, you can also derive the inverse functions. Pretty straightforward. So far, so good? Okay, so here I want to just go a few steps further using the third order Butterworth as an example. Okay, so the third order Butterworth as an example, if we just really do this substitution, h of s is known, right? H of s, but whenever you see an s, you see here is where s appears. Okay, here's one location where you see s. Replace it with s of z. Okay, and here, that's the only place, right here in this formula. But when we 把它爆开, when we expand the three terms, now you have 1, 2, and 3. Okay, this is a second order polynomial, and this is just simply s plus its first. That's where the one pole is located, and now you have this. So seriously, this is what you should do. There are three terms. Multiplication is a product of three terms. So at the bottom right here, whenever we see s, replace it with s of z. That's what we mean. Is that clear? Replace it with s of z, and that's why I say it could be pretty tedious. Right? It could be pretty tedious because now you have square, right? So things are gonna look dirty, but nonetheless, it's straightforward. Okay? It's not hard. It's just dirty. Okay, so you can do that, but that's not the end. Okay, because in the end we want this expression to be in terms of b of z divided by a of z, where b and a are both polynomials, right? But do we have polynomials here? Not yet, right? This is not a polynomial of the inverse. This is not. So we need to move some terms around so the final expression becomes b of z divided by a of z. Because this is not a polynomial yet. Okay, so we are not happy yet. So what should we do? We should try to make the bottom a polynomial by multiplying this bottom part with 1 plus z inverse to the cube to the third power. Okay, so let's multiply the top and bottom both with 1 plus z inverse parenthesis 刮弧 to the third power 三次方 So hopefully by inspection, can we agree that after doing that, after we multiply top and bottom with 1 plus z inverse, let me write it down. Just multiply now with that omega c third power over large big thing. Here is whenever I see an s, okay? S plus omega c. Actually, we've done that last Thursday, right? That's last Thursday's, that's in your homework, okay, which is due tomorrow. So whenever we see s squared plus omega c s plus omega c squared, But every s has but s equals to 2td 1 minus 1 plus, okay? So the problem is this term right here, That's giving us some trouble. This is where the trouble is, okay? So to make the final expression equal to bz, to organize the final expression into this format, we need to, I suggest that we multiply the top and bottom, just 同乘以, we multiply top and bottom with 1 plus z inverse to the third power, okay? So that here is a 1 plus z inverse. Here is a 1 plus z inverse, and here's also a 1 plus z inverse. Okay, so multiply. Just do it carefully. Okay, multiply top and bottom with 1 plus z inverse to the third power to remove, so that now the top and bottom both become polynomials. Can we do that? So that the top and bottom will both become polynomials. The bottom might look like, so this, after doing that, then b of z seems to be just omega cutoff frequency third power 1 plus the inverse to the third power. We get this, okay? But how about A of z? A of z, I will not find the final expression because your computer, MATLAB, can do it for you. Okay? MATLAB does it for you, but here the kind of derivation would be something like there's 2 over TD, 1 plus z inverse, and then plus omega c. There's also 1 plus, no, yes, no. This is minus, sorry, that's minus, okay? You know what I mean. So we use one, so here we have changes to like that. That's the first term, okay? Let me find another color. And so we move this 1 plus z inverse to here, okay? So that's using one of the 3 chances. Because where are the two other chances? 有3次机会了. So the first chance can be used right here. And then here, we should just assign 1 plus z inverse, multiply with that. And here, under this second term, we will multiply this second term with 1 plus z inverse to the square. Okay? So if we do that, then this is gone, and this is also gone, but now we have one extra 1 plus z inverse, and this has 1 plus z inverse square. So now, do we have a polynomial? Do we have a polynomial? Yeah, okay. Now, A of z is this times something square plus omega c something 1 plus z inverse plus omega c square 1 plus z. So that's A of z. We happy? Huh? Yes or no? So I said this is pretty tedious. That's why we need MATLAB or Python or any library, okay? But theoretically, you can just complete this calculation. We're not happy yet, actually. Why not? Okay? Anybody tell me that this is not yet A of z? And this is actually not yet B of z. Something is wrong. One tiny little bit. The inverse is, or reverse is everywhere. This is polynomial for sure. This is polynomial, this is also polynomial, but the leading coefficient of A of z, 首次的系数啊，常数项数 the constant coefficient of is not yet 1. So if you find the corresponding difference equation, that's okay. Please normalize. Then still, should I say this is A? Not yet. A, this is, can be say this is A. I don't know. I'm running A almost. A 几乎啊 ，A 几乎 ，A sub 几乎啊 ，B sub 几乎啊。But then we still need to normalize so that A becomes, let's say, A of z. The final A of z should be A 几乎啊 ，A 几乎 of z divided by some kind of constant, okay? So that A of z is equal to 1 plus something z inverse plus something. It's a third power, so we have 4 terms. Something. Now, usually we like the first coefficient to be 1. Okay? So that the corresponding difference equation is in the right format. Okay? So the tiny little details, okay, just for your reference. For us to appreciate this. Could be tedious, but it's nonetheless not hard. It's not that hard. Okay? Any questions so far? Yeah, we can do it. Follow the steps, substitution, organization, and renormalize so that A of z has a leading coefficient of 1. Then everything should be fine. Okay? Yeah. Okay, so you can design a third order, but still, this is just about calculation. But next, we want to just study a few properties of a bilinear transformation so that we can be convinced that this really gives us a good design. Okay, this difference equation really has basically the same frequency response as our analog prototype. Okay, why can we call this a design? Okay, well, why can we call it a design? So there are a few properties that we can be aware of. The first property is that since bilinear transformation is a mapping between S and Z, so the first most important property to know is that the imaginary axis in the S-plane will be mapped to the unit circle of Z-plane. Okay, so let me just draw it. So let's imagine that you are going like bottom to top, going in this direction along the imaginary axis in the S domain. Okay, imagine that going up, you walk along like that. Then transforming to the Z domain, the path, the contour becomes a circle. Actually, the unit circle. We have, I believe, have we shown that? Yeah, it's also part of your, it's a part of your homework. I forgot, but it's rather easy to show. It's rather pretty easy to show. Okay, it's rather pretty easy to show. You just need to show that. But that's a result. Okay, it's going, and I mean the imaginary axis is mapped to the unit circle. Okay, yeah. That's property one. Okay. So let me just introduce all the properties before we dig into details. Okay. So that's the first property I claim to you. Yeah, that the bilinear transformation is a mapping between S and Z, and in particular, the imaginary axis is mapped to the unit circle. So therefore, this implies a relation between big omega and small omega. You can make a derivation. Yeah, you can make this derivation. I believe we've done that last Thursday, okay, in both sessions. Chinese or English session, we've seen this, right? There's a relation between big and small omega, where big omega really is radian per second, small omega really is your DSP, okay? Is the omega in DTFT. It's really the omega in DTFT. Okay, there is this relation. Okay, so quickly, I think we should just show it to make sure that we understand what's going on. Okay. So how do we show it? Let's say which direction should it go? I think it might be easier this direction, okay? So let's keep this. Let's say from here, that's Z as a function of S, okay? So if S is J omega, where does it go? Where is this mapped to the Z to the Z plane, right? So we just substitute S with J omega in right here. Then here we get Z equals to 1 plus J TD divided by 2 big omega divided by 1 minus J TD divided by 2 omega. And it's rather easy to show that Z. Now, therefore, first of all, Z has a length of 1. So just by this very simple argument, we have already shown that the imaginary axis is mapped to the unit circle. Right? Because whenever if S is on the imaginary axis, then Z is on the unit circle. Yeah. That's what we are showing. Is that clear? If S is on the imaginary axis and you write it as S equal to j omega, then Z absolute value is 1. That implies Z is on the unit, somewhere on the unit circle. So then our next job is to find out exactly where. We say somewhere. From now, it's already pretty obvious that it will be on the unit circle because that absolute value is 1, right? But now technically, where exactly on the unit circle? That's our question. That becomes our question, right? Yeah? So if you're with me, next, how do we find out exactly where on the unit circle is S mapped to? Right? To where? To which point is S mapped? Okay. So now if Z is on the unit circle, we can say Z equals to what? Equals to E to the J small omega, right? Parameterize, we can parameterize the unit circle. Let's say we are interested in find out this angle, okay? If given a point, any point j omega right here, where exactly on the unit circle, what's the angle? What's this angle? If S is j omega, okay? What is this angle? What is this angle? Okay? And from here is probably the way I like to write it is that now this angle, since right here we have a division, right? We're dividing one complex number by another complex number. Therefore, the result, the angle of the result should be the difference, should subtract. You should subtract the angle of this term from the angle of that term. Take the difference because we're dividing complex numbers. So the angle goes through a subtraction, okay? So what I mean is that this angle should be the first angle on top. This complex number has an angle minus the angle of actually its complex conjugate. Okay. So therefore, what is this angle? The angle right here is exactly arctangent of the imaginary part divided by the real part, which is 1. And similarly, the angle here is just minus arctangent TD omega divided by 2. So that's why. Just imagine that we have two complex numbers, okay? And we know that the angle of one complex number is arctangent. It's quite kind of nice to be reminded that the angle of any complex number is arctangent of imaginary part divided by the real part. So now, finally, you have a factor of 2. 2 arctangent TD omega divided by 2 equals to what? Oh, equals to omega. Yeah. Omega being, where is this angle? Okay. So since small omega, we can now is a function of big omega, and the inverse function exactly is that. Okay. Then big omega, small omega. Okay, we have this very nice relation. Okay, and which we'll come back. Okay, well, this is important. Okay. Now we have a one-to-one mapping basically between small and big omega. Right. So far so good. So that's a derivation where I think our presenters last Thursday also showed the same kind of thinking process. Okay, same thinking process. Because of bilinear transformation, we have checked that the imaginary axis in the z domain is mapped to the unit circle. and there's a relation between small omega and big omega. There's a one-to-one mapping. The one-to-one mapping between the entire imaginary axis and the unit circle. Okay? Now, should not be surprising, right? Does anybody find this surprising? Historically, it could be surprising, okay? Because now it's a very good example of mapping an infinitely long line to the circumference, 到圆周. But the circumference has a finite length, right? The arc length is 2 pi r, 2 pi. So we are mapping an infinitely long line to the circumference 圆周 of the unit circle, which has a length of 2 pi. But that's a natural property of the tangent, right? Tangent does that. Tangent does that, okay? Or the other way around, tangent maps the finite interval of 2 pi to entire, the set of the entire set of real numbers, okay? Infinite line and finite interval, okay? You can find a one-to-one mapping like that. You can construct a one-to-one mapping between a finite interval and an infinitely long line, okay? It's doable. Tangent does that exactly, okay? So that's a very useful relation, and yeah, this is the first property. And going from the first property to the second property, okay? I want to invite you to think about, let me read it, okay? Turns out that the bilinear transformation is also one-to-one mapping between the left half plane in S and the inside of the unit circle. The left half, right here, the entire left half plane is mapped to the inside of the unit circle, okay? And you can also show that. Okay? But intuitively, this is a kind of a nice property about orientation of a contour. Okay? I say orientation of contour. 那个轨迹啊，它可能有一个方向性啊。Orientation. How do we explain? So we know that S is a function of Z, or Z is a function. Yeah, let's say Z is a function of S here. Okay? Z as a function of S. Going from S to Z domain, okay? So the principle is that this is a property of complex function with a complex variable, okay? 复变的一个 basic property, which says that if you have a kind of closed contour and the orientation is counterclockwise, okay? And you take it from S to Z. In general, if your mapping is so-called analytic function, 解析函数 if f of s, if z equals to f of s is analytic, in the sense of Cauchy-Riemann symmetry, okay? In the sense that its real part and imaginary part obeys the Cauchy-Riemann relation, 柯西黎曼的关系 analytic function, so it becomes differentiable 这类的 If you have a differentiable function, and which is this differentiable? Yeah, almost everywhere except at this pole location, okay? But everywhere else, z is a differentiable function with respect to s. 对 s 是可微分的。Under the meaning of here, really everything is complex numbers. So if Z is analytic, then when you start in the S domain, going around the contour in this orientation, let's say counterclockwise, then it turns out that in the Z domain is should be also counterclockwise. The Z domain, the shape can change. The shape can even be ugly, okay, but still it's counterclockwise. And furthermore, what stays on the left? What is on the left stays on the left. Left-hand side is still the left-hand side. Inside is still inside. Outside is still outside. If I understand correctly, okay, inside should still be mapped to the inside, okay, outside to the outside. Okay, so, all right, good. So I want to invite you, okay, to think, but now here, this is not a closed contour, right? As imaginary line is an infinitely long line, right? But let's apply this this property. What's on the left-hand side should still be in the left-hand side after the transformation, okay? So left-hand side of the imaginary axis obviously should be the left half plane, right? But how about the left-hand side of this contour? If you go counterclockwise, what's the left-hand side? Is the left-hand side inside or outside? If you go around the circle like that, your left-hand side is, imagine you're going, right? You're an ant, or a bug or snail or whatever, or a snake or a lizard, okay? Going around, what's your left-hand side? Left-hand side is inside, right? Left-hand side is mapped to left-hand side, okay? That's a pretty basic property about functions of a complex variable, okay? And this has a nice implication, okay? This has a nice implication, which is point number 4. But let me explain. There's a third property, okay? Now, the next property is that, in general, this equation 1, I say, is analytic, okay? And an analytic mapping, an analytic function defined on the z-plane, has a property of being conformal, okay? This mapping will be a conformal mapping. Conformal mapping, have you learned that? Have you learned the concept conformal mapping? Have you heard of it? Yes? No? Have you heard of conformal mapping? Yeah. Conformal mapping in Chinese is 保角变换. It means that somehow the angle is preserved. Literally, 保角嘛，保持角度, the angle is preserved. In what sense? In the sense that, imagine if you have two vectors. Yeah. Imagine again that we are on the, let's say, if we are on the S-plane to begin with, yeah, either way. So let's say this is the S-plane. And at any given point, any random point on the S-plane, okay, imagine that you can go in an arbitrary direction, start moving with a infinitesimal step, 一小步, 跨出一小步, just going along a certain direction with an infinitesimal, really, really small, let's say S and ds. And this is ds1, okay? There's one possibility you can start at this location S and go one tiny small step toward a certain arbitrary direction, okay? And you can also go toward another arbitrary, now I'm drawing a really big, but imagine this is a very small step, okay? Just for the sake of drawing, I make this arrow a long arrow. But two infinitesimal directions, two very small steps along S1 direction or S2 direction, and there's an angle. Let's say the angle is difference is phi, okay? Yeah. That clear? Yeah. So now we have an analytic mapping, which is z equals to 1 plus td divided by 2 divided by s, 1 minus td divided by 2 multiplied by s, okay? This is an analytic function defined on S, okay? So we said that this transformation now going to the z domain should preserve the angle phi. So that means now going to the z domain, first of all, going to the z domain, S will land somewhere in the z domain, okay? Let's say S now is located right here. Doesn't really matter. Z of S, okay? But now, how does this small move? How about this small move? Okay, so by moving from S to S plus ds1, so now the corresponding move might be in any direction. Okay, so z of S plus ds1. Okay, z as a function. Here, z is a function. Okay, z as a function. Now this point also move infinitesimally, one very small step toward a certain direction. Okay, and then how about S2? Now z can also move toward a certain direction. This is z of S plus infinitesimal ds2. But now, in general, these two directions are not going to be same as these two directions, okay? But what remains the same is the angle in between the two directions. That's what we mean conformal, okay? This angle phi is preserved after the transformation, okay? If a transformation has this property, then we say that the mapping is conformal. We have a conformal mapping, 包角变换. And this is something deeply rooted in the fact, this is a consequence of the fact that z is differentiable. Z as a function of S is differentiable except at its singularity. 它可能有基点起点 singularity, except at one singularity. Otherwise, everywhere else, z is a differentiable function of S. Therefore, it preserves the angle like that. It is a conformal mapping. Okay? So why do I want to mention this? In tomorrow, any questions so far? So far so good. Conformal mapping. Tomorrow, I invite you to think about, all right, now, the imaginary axis is mapped to the unit circle, and the left-hand side is mapped to the left-hand side, which is inside. But how about, turns out that all the lines, all the straight lines, such as all the lines parallel to the, parallels to the imaginary axis, to the left or to the right. All the straight lines, turns out, will be mapped to a circle. And left-hand side mapped to the left-hand side, okay? So all these straight lines are going to be mapped to smaller circles inside the unit circle. Okay, so in tomorrow's discussion, I asked you to find out what exactly they are, okay? You can find out the expression. Straight lines are mapped to circles. And also horizontal straight lines are also mapped to circles. So we have two families of circles, okay? And the angle should be preserved. Okay, so here, all the vertical lines and horizontal lines are crossing each other at right angle, 直角, 对不对? Right angle. But here, I suggest you can find out that all the circles corresponding to the vertical lines and the other family of circles corresponding to the horizontal lines, they're also perpendicular. 垂直的, you will find two families of circles which are perpendicular everywhere they meet. In Chinese 是你会发现有两组圆到处都互相正交 kind of a nice property. I invite you to think deeper, dig deeper in this. It's a very nice example of what it means for mapping to be conformal, preserving the angle. Right angles right here in one domain, right angles in the other domain. Okay? 对人生没有帮助 but it's kind of nice to know. Right? So tomorrow I invite you to, when we come back, I invite you to dig deeper on conformal mapping. So yeah, left-hand side to the inside, imaginary axis to the unit circle, okay? So let's finish this slide before we take a break, okay? Yeah, so 1, 2, 3. How about the fourth property? The fourth property has is a property about stability. Okay, so let me read it. Now imagine that since the left-hand side is mapped to the inside, okay? So remember that when we design the prototype in the S domain, when we design the prototype in the S domain, we draw a big circle with radius omega c, right? And we are placing poles right here by cutting pizza, kind of, yeah. Cutting pizza. Okay, yeah. So we place the poles on the left half plane in S domain. We didn't emphasize this, but there's a reason why we put the poles to the left-hand side of. We place all the poles to the left of the imaginary axis. So as what's the purpose? The purpose is so that the analog prototype corresponds to a stable system. Okay, if you apply the inverse Laplace transform, the impulse response converges to 0 when t goes to infinity. Okay, we begin with a stable design, stable analog design. This system is not going to oscillate or doing anything funny like that. Okay, you begin with all the poles to the left of the imaginary axis so as to ensure stability. That's in the analog domain, in the S domain, analog domain. But when we go to discrete time, now it's good. It's kind of comforting. 让我觉得受到安慰啊。It's really nice that all the poles here are going to map where? They're going to be mapped to the inside of the unit circle. Okay, so now from S to Z, this is Z plane. Now these poles, wherever they are gonna be in the inside of the unit circle. Might be something like that. We have equally many poles now in the Z domain, but all of them are guaranteed to be inside the unit circle. And isn't that great? It is great, right? Make the response great again, right? Because if all the poles are still inside the unit circle in the Z domain, we know that this system, this corresponds to a stable and causal system. Yeah, none of the poles will go outside. Okay, so that's pretty nice. Stability is preserved under bilinear transformation. Let me repeat that. Stability is preserved after bilinear transformation because all the poles are going to go inside the unit circle, okay? To ensure that now our design, which I just erased, 我们刚刚擦掉了, that design will be a stable system because all the poles are now inside the unit circle in the Z plane, on the Z plane. Okay? Stability is preserved. Stability is preserved. And that's pretty important. Every time we have a singularity in the Z plane, then after transformation, the singularity goes there, which is inside the unit circle, given that S is to the left-hand side of the imaginary axis. Okay? Therefore, stability is preserved after bilinear transformation. Very strong property, strong and important property, useful. And then finally, we have shown that. Okay, we have shown that because of that kind of tedious work, B of Z will contain a factor of 1 plus Z inverse to the n power on top, B of Z, okay, B of Z on top in the numerator, okay, in the numerator part, has a factor of 1 plus Z inverse to the nth power. Or in other words, we have the case of a multiple root. Okay, we have a place of we have the case of a multiple root of B of Z. Okay, B of Z basically will be exactly 1 plus Z inverse to the nth power. Okay, yeah. So let's take a break. Okay, so when we come back, then we look further what this implies. Okay, about this relation between big omega and small omega.